I want to take you back to Physics 20. In Physics 20, we solved questions that looked like this a number of times. We call those roller coaster problems, right? Car starts at rest at the top of a hill. Maybe the hill is 10 meters high. We wanted to find the speed at the bottom of the hill. You guys remember those problems? You saw one of those, well, you would have saw one of those on a quiz. You saw one of those on your unit test, your dynamics unit test in Physics 20. And you also saw one of those on your final exam in Physics 20. For the most part, we did a good job on those questions. For the most part, we understood those questions and we could solve those questions. We solved these questions using a concept called conservation of mechanical energy. That law of conservation of mechanical energy says that energy can't be created and it can't be destroyed. It can only be transformed from one type to another. In other words, we said EI was equal to EF. The total initial energy is equal to the total final energy. Remember that? All right, let me ask you a few questions about this. See what you remember, the details about this from Physics 20. What type of energy does this car have at the top of the hill? It's not moving, but it's at the top of a 10-meter high hill. What type of energy does it have, Ed? It's got potential energy, right? And that potential energy is mgh. Does it have kinetic energy at the top of that hill? No, it doesn't. How come not? It doesn't have potential energy? Or I should say, how do you know it doesn't have potential energy, kinetic energy? Good, because it's not moving. So it's got potential energy because it's got a height. It does not have kinetic energy because it isn't moving. Good? All right. Well, what kind of energy would this car have at the bottom of the first hill? Once it's accelerated down the hill, it no longer has a height. David? We would have kinetic energy at the bottom of the hill because it's moving. Would we have potential energy at the bottom of that hill? No potential energy at the bottom of the hill because there's not a height. Good? So this is a relatively straightforward Physics 20 problem, right? Let me ask a couple more questions about that. What type of energy did we lose in this process? Potential energy, right? Potential energy decreased. What type of energy did we gain in this process? What kind increased? Yeah. Kinetic energy increased. What didn't change through this whole process? Potential decreased, kinetic increased. Yeah, the total energy didn't change. The total energy stayed the same through this whole process. All right. Now, let me tell you why I went back to this Physics 20 concept. This isn't a Physics 30 concept per se, but we're going to relate it real closely to a Physics 30 concept. Let me draw a new picture now. This time, instead of having a hill, we have two charged plates, a positive plate and a negative plate. This time, instead of having a car at the top of the hill at rest, we have a positively charged particle at rest. This time, instead of having a height of 10 meters, difference between the top of the hill and the bottom of the hill of 10 meters, let's say we've got a potential difference of 20 volts. The difference in energy per coulomb of charge between the top of the hill, between the top plate and the bottom plate of 20 volts. Make sense? I don't know about you, but when I see this question, I have trouble visualizing this. It's not quite so every day as a car going down a hill, right? If I try real hard, maybe I can kind of picture it, but I have a much easier time picturing a car going down the hill. Would you agree with that? Yeah. So what I want to do with this question is turn it into a car going down the hill problem. I can see that car going down the hill. I can't see this. If this is a car going down the hill, Ed, are you picturing this car going down the hill? Yeah? What color car is it, Ed? Blue? Okay. Bigger car, smaller car? Smaller. So a smaller blue car. Can you see it? Can everybody else see this smaller blue car? Ed, is it newer model or older model? Older model, okay. Older model, small blue car going down the hill. Okay, can you see it, guys? Ed, how many people inside? Just one? Boy or girl? Can't tell? Okay, too far away? Okay. Okay. So we've got one person inside this smaller, older model blue car going down the hill. Everybody see it? Okay, that car is going to speed up as it goes down the hill, right? Just the same as this positive particle is going to speed up. Look, it's being repelled by the positive plate. It's going to speed up as it goes toward the negative plate. Agree? Picture it as a blue car, older model, small, one person inside going down this hill. What kind of energy would this smaller, older model, blue car with one person inside have before it accelerated? At the top of the hill, in other words, what would it have? Potential energy. Don't write this down quite yet because you'll see why in a second, okay? What kind of energy would this car have when it's reached the bottom of that hill? Kinetic energy, right? Well, there is one small problem with this, and that is that the energy that we're dealing with here, the potential energy that we're dealing with, isn't gravitational potential energy anymore. It's, no, electric potential energy. So we have to replace mgh with an equation for electric potential energy. Otherwise, it's the same question, right? In fact, what I suggest you do, every time you see a charged particle speeding up, every time you see a charged particle speeding up, picture it as the blue, small, older model car with one person inside going down the hill. Picture it as a car going down the hill, because we know at the top of the hill that car has potential energy, and at the bottom of the hill it has kinetic energy. All we're going to do is replace mgh with the equation for electric potential energy, which is Q times V, charge times electric potential. Otherwise, exactly the same problem, right? Now, where does that equation come from, Q times V? If you remember, we talked yesterday about electric potential difference. We defined it as energy per charge, energy per unit charge. In other words, delta E over Q. That's the definition for electric potential difference. It's an equation, and that equation is on your data sheet. If we rearrange this, solve for delta E, we get Q times potential difference. If we drop the delta, it's not delta E, it's just E, then it would be Q times potential. Potential difference versus potential. That's what this is, Q times the electric potential, the initial electric potential. Okay? Now, what if I change this up a little bit? Oh, sorry, before I do that, let's answer the same questions over on the right-hand side. What kind of energy do I lose here? As a charged particle speeds up, I lose what? Picture the car going down the hill. What kind of energy does the car lose as it goes down the hill? Potential. Okay, so I lose potential energy as a charged particle speeds up. Except it's not gravitational potential, it's electric potential. What kind of energy does the car gain as it goes down the hill? Car gains kinetic. Okay, well, what kind does a charged particle gain as it speeds up? Kinetic. What stays the same? What doesn't change? Well, in the case of the car, it would be the total energy. What doesn't change in the case of the charged particle? Total energy. It's exactly the same thing, right? Except for mgh getting replaced with Q times V. Okay, let's up the ante a little bit, make it a little bit harder. Let's say this time, instead of the car starting at rest, 0 meters per second, let's say the car has an initial speed of 15 meters per second. What kind of energy does the car have at the top of the hill now? Picture it. Small, blue, older model car, one person inside. Where's the person going? Okay, down the hill. What's at the bottom of the hill? Walmart, okay. Older model, small blue car, one person inside, going down the hill, going to Walmart at the bottom of the hill. What kind of energy do they have at the top of the hill now? Potential? Yeah, because it's still a height. Kinetic? Yeah, because it's moving now, right? So we're going to add in mgh plus 1/2 mvi squared. What kind do we have at the bottom of the hill? There's Walmart right there. Bottom of the hill by Walmart. What kind do we have? Kinetic energy. Same deal over here. Instead of starting at rest, let's say that this car or this charged particle starts at a speed, I don't know, let's make it 1.5 times 10 to the 4 meters per second. Charged particles usually moving faster than cars. 1.5 times 10 to the 4 meters per second. We're still picturing it as a small blue older model car with one person inside going down the hill to go to Walmart, right? but this time the car is moving at the top of the hill before it speeds up. What kind of energy do we have at the top of this hill? Do we still have potential? Yeah, but it's QV potential, not MGH potential, right? Do we have kinetic? Mason, do we have kinetic? Yeah, because it's moving. Do we have kinetic? Do we have potential at the end of the problem when it's got to the bottom of the hill and is moving as fast as it's going to move? If we've gotten to Walmart, do we still have potential? Nope. Do we have kinetic energy, Sunil? Do we have kinetic energy at the bottom of the hill? Yep. So it would be 1/2 mvf squared. Good? Okay. Let's make it even harder. Although if you get this, you're on your way here. Let's make it a bit harder though. Let's say this time, instead of trying to find the speed at the bottom of the hill, let's try to find the speed halfway down the hill. So we're still in a smaller, older model, blue car, one person inside, going to Walmart at the bottom of the hill. But we're not trying to find the speed at the bottom. We're trying to find the speed halfway there, halfway down the hill. Do we still have potential at the top? Yep. And we still have kinetic at the top? Yep. What about at the bottom? Do we still have kinetic? Not at the bottom, but halfway down. Do we still have kinetic? Yeah, because it's moving, right? Do we have potential halfway down? Yes, we do. MGH potential. What would the value of HI be there? What's the value of the initial height in this problem? Yep. 10 meters, good. What's the value of the final height, assuming that we've gone exactly halfway down the hill, Yana? 5, good. Does that make sense? You've solved almost that exact problem in Physics 20, right? Well, let's move it over here. This time we want to find the speed of the particle halfway across. Do we still have potential to start off? Yep. Except it's QV potential, not MGH potential, right? Do we have kinetic? Yep. What about when it's halfway across? Do we still have kinetic when it's halfway across? Yep. Yep, we do, because it's moving, right? Pick on the person that's drinking water. Do we have potential when it's halfway across? Yeah, except it's QV potential, not MGH potential, right? What would the initial potential be there? What would the initial potential be in this question? 20 volts. What would the final potential be? Nope, not 20 volts. 10 volts. We've gone halfway across, right? Make sense? I'm going to tell you something. I hope I don't confuse you with this. I want you to understand this better. We're given the potential difference of 20 volts. Got it? The potential difference of 20 volts. We said the initial is 20 and the final is 10. We weren't actually told the initial is 20 and the final is 10. We didn't have to put in 20 and 10. We just did. So what if I do put in 20 and 10 and Michael puts in something different? What if for whatever reason, for some odd reason, Michael puts in 35 for the initial potential? What should he put in for the final potential? 25, because he's gone halfway across 20 volts potential difference. Does that make sense? The difference between the initial and the final potential for us needs to be 10 volts in this question. It doesn't matter whether the initial is 20 and the final is 10, or the initial is 35 and the final is 25, or for that matter, the initial could be 10 and the final could be 0, as long as the difference in potential is 10 volts. Does that make sense? Why 10 volts? Because we've gone halfway across a 20 volt potential difference. Probably makes sense to go 20 and 10 just because of the nature of the question. Just know that we're not actually given VI and VF. We're just kind of making them up, values that are convenient that fit. Yep. Yeah, no, that's a good question. If we said the initial was 35, then the temptation would be to say the final was 17.5, right? We're not halving that. We're halving the potential difference. The potential difference across from the top of the hill to the bottom of the hill is 20. So half of that is 10. So the difference between the top and the middle is 10. Whatever you make the top, the middle is 10 less. Does that make sense? Probably makes sense to go 20 and 10, right?
And then with the bottom be like that after at the very bottom would be like 15 if we're using 35.
Yes. If you start with 35, the very bottom would be 15, yes. Or if you started with 128, the very bottom would be 108. Of course, when you're doing the top and the bottom, it really makes sense to go 20 and 0, right? Mathematically, it's a lot easier if you do that. But it doesn't matter, as long as the difference between the very top and bottom would be 20, or the difference in this question is 10. Okay? All right? Let's do an example here with some real numbers and some real calculations here. Example number 1 says an electron is released at a speed of 1 times 10 to the 5 meters per second at a negatively charged plate, accelerates toward a positive plate. This whole sentence is pretty important. What's happening to this charged particle? What's happening to this charged particle? It is, well, it says it's released at this speed. So it's released with a certain speed, right? But what happens to it? I'm not asking like, what does it look like when it's released? I'm asking what happens to it. Like throughout the problem, does it speed up? Does it slow down? Does it stay the same speed? If you release something at a negatively charged plate, and that thing is negative, it's going to be repelled by it, right? So if it was moving at 1 times 10 to the 5, and it's repelled by the thing that it's at, it's going to speed up. It's going to speed up, right? Don't picture it as the charged particle speeding up, though. Picture it as the small, older model blue car with one person inside. It's going to Walmart at the bottom of the hill, going down a hill. Picture the car going down the hill. That's what's happening here, right? Charged particle speeds up. That's exactly like a car going down the hill. We're looking for how fast is it moving when it's halfway across the plates. So halfway down the hill. We're going to say the initial energy does it got potential? Speeding up. Does it start with potential? Picture the car. Picture the car. Does the car at the top of the hill have potential? Yes, except in this case it's not MGH potential, it's QV potential. Does the car at the top of the hill have kinetic energy? Yeah, in this case it does because it's moving, right? So we're going to add kinetic energy to that. Halfway down the hill, does the car have potential energy? Yeah, still got a height, right? Well, we're going to replace it with QV instead of MGH, but same idea. And of course, it's still moving, so it's got kinetic energy halfway down as well. Somebody in the last class said, can we cancel out the M's? We could do that in physics 20, right? Can't do it here, because in physics 20, we dealt with kinetic and gravitational potential, where M appeared in every term. Here, M doesn't appear in every term, so you can't cancel it. Okay, let's sub in some numbers here. 1.6 times 10 to the minus 19. What's my initial potential? We don't really know. What does it make sense to make your initial potential? Probably 20, right? Like you could make it 58. You just have to make VF consistent with it. Makes sense to probably make it 20. My initial potential is 20 volts plus 1/2 of the mass of the electron times VI, which is 1 times 10 to the 5 squared. What's VF? We don't really know. But if we made VI 0, we made VI 20, then VF would be, we've gone halfway across, would be 10, right? Our potential difference is 20, so we've gone halfway across that. We have to subtract 10 from the initial of 20. My mass is 9.11 again. Man, this is a long one. And we're solving for VF. Would you expect VF to be bigger or smaller than 1 times 10 to the 5? Car's going down a hill. Speeds up, right? It's bigger. Remember, we lost potential, we gained kinetic energy. Okay, let's see what we can do with this. Let's get the left-hand side here. Let's say 1.6 times 10 to the minus 19 times 20. There's the first term. Let's add that to bracket 0.5 times 9.11 times 10 to the minus 31 times 1 times 10 to the 5. Bracket. Okay, there's the second term on the left side. Okay, good. What are we going to take over to the left side next? David? The what? Yep, this green term here, right? And we're going to take it over by what? Yes, we're adding it to the right side, so we're going to take it over by subtracting. Good. So let's move the calculator over here. Let's subtract now from the left-hand side. Bracket 1.6 times 10 to the minus 19 times 10. Now everything's on the left side except for the 1/2 9.11 VF squared. Let's take the half over by multiplying by 2. Let's take the 9.11 over by dividing. And then how do I get VF by itself? So root it, yeah. 1.9 times 10 to the 6. Is that too much together there? Or do you guys need the individual steps along the way? Was that okay? 1.9 times 10 to the 6, that's faster than 1 times 10 to the 5, isn't it? Should be faster, shouldn't it? And it is. That seems reasonable, doesn't it? What if I had gotten 1.9 times 10 to the 9 meters per second? Is that reasonable? No, because that's faster than the speed of light. Can't be faster than 3 times 10 to the 8 meters per second. If you get 1.9 times 10 to the 9, you know you've made a mistake. You know you've got it wrong. Try again. This seems pretty reasonable, though. Usually we're in that 10 to the 5, 10 to the 6, 10 to the 7 meters per second range. Yeah. It is 10 to the 6, yeah. David? It's asking you for how fast the electron is moving, so that's a speed thing, right? How fast is it moving? It's just a speed. All of these questions like this, that's what it'll be. No, because, I mean, we're dealing with energy, and energy is all scalar nature. How fast is it moving when it's gone all the way to the negative plate? All the way to the negative plate. Well, picture your car, your small, older model blue car with one person inside going to Walmart at the bottom of the hill, at the top of the hill. What kind of energy is the car at the top of the hill? Potential energy, but it's QV potential, not gravitational potential. It's also got kinetic energy because it started off with an initial speed. What kind does it have when it's reached the bottom of the hill? Kinetic energy, right? Bernardo? No, sorry, yes, good point. This was supposed to be positive plate. Yeah, I forgot to make that change. Somebody in the last class pointed that out as well, and I just forgot to make that change. It should say positive plate there. Yeah, that's a good point, though. Yeah. When it reaches the negative plate, it was already at the negative plate, right? So it's the same speed. It wasn't meant to be a trick question. It was. It turned out to be, but it wasn't meant to be. 1.6 times 10 to the minus 19 times VI, which is, we'll make it 20 volts. Did we need to make it 20 volts? No, but it really makes sense to make it 20 volts, right? VI is 1 times 10 to the 5. What else could we have made? What else could we have made VI instead of 20 volts? Give me a number for it. What else could I have done for it? Could have made it 40. Well, if I hadn't made it 40, then I would just would have had to make sure that VF was 20. I just made VF 0, right? My final potential is 0, my initial is 20. It would have been okay to say VF is 20 and VI is 40. It just would have been more math work and I think more confusing, but it would have worked. Expect VF to be bigger or smaller than 1.9 times 10 to the 6. Probably bigger, right? But definitely bigger because we're speeding up. And as we go all the way down the hill versus halfway down the hill, it's going to be speeding up even more. 2.7 times 10 to the 6 is what we get for this. So we see those two numbers. Like, we don't know for sure when we see them that they're right, but man, they sure seem good. They sure seem reasonable. Let's take a look at example number 2. An electron is released in an electric field moving at a speed of 5 times 10 to the 6 in the direction of the field. What's the potential difference required to stop it? Let's draw this out, okay? Because this is a bit confusing, right? Speeding up, slowing down, it's kind of confusing. Here's my electric field. I got to draw it to the right. We're not really told which way it is, but whatever. I'll pick a way. It's drawn to the right. I've got an electron, a negative particle right here. It's moving to the right in the direction of the field. Which way is the force on this negative particle in this electric field? You know this, right? A positive particle experiences a force to the right. A negative particle experiences a force. Good. So the force on this is to the left. All right, if it's moving to the right, but the force is to the left, what's going to happen to it? It's going to slow down. Wait a second. Cars going down hills don't slow down. Cars going up hills slow down. So we're going to treat this as a car going up a hill. Picture now that car, Ed's small, older model, blue car with one person inside, just left Walmart, sped up to 5 times 10 to the 6 meters per second, throws it in neutral, and then coasts up the hill. Got it? What kind of energy does Ed's small, older model blue car have at the bottom of the hill? Remember, it's not being powered by gas here. We're throwing it in neutral, coasting up the hill. What kind of energy does it have? Yeah, it's better to have kinetic, otherwise it isn't going to make it up the hill, right? Yeah, and a lethal potential if it's going at 10 to the 6 meters per second. You're right. It's got potential energy, kinetic energy to start. Does it have kinetic energy when it reaches the top of the hill? The car could, but if the car barely makes it and stops at the top of the hill, does it have kinetic energy then? No, it would have potential energy then. But we're not going to call it MGH potential. We're going to call it QVF potential. Let's sub in numbers for this. VI is 5 times 10 to the 6. Don't forget to square that. Drop the sign of the charge. We always drop the sign of the charge. V, remember, QV, not QE. QE is electric force. QV is electric energy. Solve for VF here. We solved for that, by the way, VF. It works out to be, I want to say it was 71.2. Yes, it was. 71.2 volts. Now, again, at the risk of confusing you a little bit, I think it's important for you to understand what's going on here. We just solved for final potential. That's not what we were looking for. What were we asked to find? Potential difference. The difference between the initial and the final. We found the final. But what did we assume the initial to be? 0. Okay, the initial is 0 and the final is 71.2. What's the change? What's the difference in potential? 71.2, right? What if we had, for some strange reason, I don't know why we would have done this, but what if we had made the initial 20? Could we have done that? Yes, we could have. Yes, we could have. What would we have gotten for VF if we had made the initial 20? 91.2. Would that have been my answer? No, my answer would have still been the difference between the initial and the final. So technically, we found the final You've got to subtract final minus initial. But since we made the initial 0, it's just the final, right? That make sense? It's just like gravity, right? We can define, you learned in physics 20, you can define the height relative to whatever you want. Right? The bottom of the hill is 0 meters. You could have made the bottom of the hill 20 meters, as long as everything is defined relative to the same spot. This is no different, okay? All right, the questions that I'd like you to work on for this, we'll say for Monday, and you can finish them in class maybe. Worksheet number 9. Questions 1, 3, and 5. There's more questions on this page, but I think if you can do 1, 3, and 5, I think you're going to be in decent shape, certainly for the first day of this. So questions 1, 3, and 5, worksheet number 9.